Hi, everybody. I'm Jessica, as you've just heard, and I'm one half of a design studio called Nervous System. Nervous System works in many different materials, and we make a myriad of different types of products, from jewelry to clothing, furniture, jigsaw puzzles, and even sometimes at the scale of architecture. And we work in a variety of materials, everything from 3D printed steel to plastic and rubber, and even traditional woodworking and traditional metalsmithing. A lot of people often struggle to define what it is we actually do. They want to put a label on it, like you're a jeweler or you're a furniture maker. But actually, what unites our body of work isn't the type of products we make or the exact materials that we work in, but more our generative design process. Our medium is really computation. And more specifically, we focus on using computation to adapt processes and patterns from nature into design tools. Now, you might be wondering, what does that mean? And so I'll give you a very concrete example. These are dendritic crystals. The one on the left is dendritic agate, and the one on the right is dendritic limestone. And the branching patterns that you see were initially mistaken by scientists as fossils of some long-dead organisms, but actually they're inorganic growths that form as mineral solutions of manganese and iron flow through cracks in stone. The branches grow through a process known as diffusion limited aggregation. The idea is that there are particles in diffusion. That means they're just moving around randomly, which is really the basic state of all molecules. And as these particles move around, they hit something, another particle, they stick to it. And this idea is extremely simple, but when you repeat it hundreds of thousands of times, it results in these fractal branching structures. That can describe all sorts of formations, from those dendritic crystals to certain types of coral growth and other naturally occurring structures. One of the most appealing aspects of this system is it's extremely simple. As I just explained it to you, that sort of human legible description can be directly encoded into software. Once we have a system in place, we can quickly generate hundreds of designs. We can experiment with parameters, make slight modifications to our algorithm, and introduce design constraints. We use tools like these to create products like these dendrite necklaces. These are fabricated in stainless steel using photochemical etching. So far, we have sold over 5,000 of these, and every single one is unique. We never make the same pattern more than once. In order to produce these kinds of unique one-of-a-kind products, we need to use fabrication techniques that allow for the production of one-of-a-kind designs for the same cost as cookie-cutter ones. Mass production doesn't work for this. Computer-controlled manufacturing, on the other hand, techniques like laser cutting and 3D printing, open up a range of new possibilities for making. They enable us to make incredibly complicated shapes easily that'd be challenging to make any other way. They make it possible to create one-of-a-kind designs, like those necklaces I just showed you, for essentially the same cost as mass producing them by some other way. And they're increasingly lowering barriers to creation. They're people's offices, public libraries, and even sometimes now people's homes, putting high-quality, robust, accurate fabrication in the hands of more people than ever before. However, this is the hype. This is what you hear in the news. This is much more of the dream of what we want these tools to be than the reality of what they are today. And really, a super important part of this process is missing, and that's actually software. How do you define the things that you want the machines to make? Design software turns out to be incredibly expensive, very difficult to use, and it doesn't take advantage of the powerful ability to have complexity and variation that these new digital manufacturing tools allow us to do. So part of what we do at Nervous System and with generative design is explore creating new types of playful design experiences that leverage simulation and web technology to make it possible for anyone to create with these digital fabrication machines. Our design systems are inspired by complex dynamic processes that we see in nature. These processes grow and adapt to different conditions, and the resultant shapes are expressions of those processes and the conditions that generated them. The idea of form as a process is an interesting counterpoint to how humans normally create designs. We tend to take a very top-down approach. Computers are often touted as powerful new tools that offer new ways of making, but most design software tries to reproduce the methods by which we made things before computers. We have software that gives the experience of drafting or sculpting or painting, and they translate how humans have traditionally worked with physical materials into a strange digital analog of those experiences. Generative design proposes a different direction. We take inspiration from nature's process-based systems and focus on developing interactive processes that we can engage with. Instead of creating static designs, we create dynamic systems. And instead of drawing structures, we're interested in growing them. So let's look at biology. How do organisms go from a single cell to a complex differentiated structure? If a single cell were just to divide and grow uniformly, that would actually just result in a formless blob. However, what we see in biology is that through carefully coordinated subdivision and differentiation, biological systems can create structures with very specific forms and functions. I'm going to call this idea differential growth. Essentially, some areas of a structure are growing more than others, and that produces a shape. But what's the relationship between growth and form, and how is growth controlled? This might be sounding kind of abstract again, so let's look at a concrete example you experience in your everyday lives. What about plant tropisms? A plant can redirect its growth towards sunlight through differential elongation of cells on either side of a stem. What we get is a sort of gradient of growth in response to a gradient of an environmental signal, light, and that's leading to curvature, a shape that is growing into. You can apply the same idea to surfaces by looking at, let's say, two layers of cells. One of the layers is growing faster than the other, and that produces a sort of cup-like shape. This project got started, which is called Floriform, which I forgot to mention, when I came across a paper by a professor at Harvard named Mahadevan. He was studying a really interesting surface-based model of differential growth, looking at the shapes of leaves and flowers. And he hypothesized that the sort of ruffled shapes that you see on the edges of these surfaces could be described simply as a surface that's growing faster at its edge. His model is fascinating to me because you end up developing a very complex surface with this curvature that varies all over the place from a very simple procedure, grow more at the edge. And again, if you take a walk outside, look around in nature, you're going to see this everywhere. Flower petals, cabbage, lettuce leaves. But not only in plants, also sort of in all branches of life, you see these types of forms, from lettuce sea slugs to certain types of fungi and crusted cactuses. This type of differential growth described in this algorithm seems like it could be responsible for sort of the types of shapes we see in all biological life. So we built a computational system for exploring this type of differential growth. Our system is a physics-based simulation of an elastic surface, and we control the rate of growth on our surface, and we're expressing that by this color. So throughout the videos, I show you things that are more red are growing faster than other areas. So when we start developing a system like this, one of the first things we do is develop different sort of idealized scenarios that we see in our sort of model organism, in this case, plants. So here we're looking at different spatial distributions of growth and how that affects the final shape. This one that you just saw is sort of our ground truth. It is undifferentiated growth. Everything on that surface, none of it is red. It's all growing at the same rate, and that, as I previously explained, just actually leads to chaos. Undifferentiated growth gives you a wrinkly blob. Here, however, are 3 examples where the video is not going. Here are 3 examples, again, of the same surface, but with different distributions of growth. And we'll see how that produces these sort of 3 different stereotypical forms. When we're going from a point that splits, that actually gives us something that approximates a tree. However, if we're just growing from the edge, in this scenario, that's giving us this convoluted form similar to a coral. So these are sort of maybe our touchstone points for where we're starting exploring the system. After we've begun to construct a system like this and establish these baselines, how do we work with it? I describe our practice as almost a kind of digital gardening, except for instead of growing plants, in this case what we're developing is algorithms. Throughout our work, there's then this interplay between the innate behaviors of the dynamic systems that we create and our manipulations of those systems as we try to tweak the system for design. And as we're developing our software, we encode sets of influencers, gradients, and manipulators that enable us to sculpt the growth and work with it. Some of these include things like the material properties, the resistance to bending of a surface, or the thickness or scale of that material. They may also be things that approximate environmental conditions like gravity or sunlight, and its effect on the system. Or in this system, particularly what we control is the distribution of that growth signal, how that's spread out on a surface, how that diffuses across it and changes through time. Gotta breathe. At Nervous System, we disseminate a lot of our ideas through affordable objects. So we're not doing this just as research, but we turn these into products. And we've used fluoroform to grow a jewelry collection. So for each piece of jewelry in the collection, we constructed a specific algorithm that results in a specific form. We feel strongly that ideas about science and technology shouldn't just be limited to academia or theoretical projects, but should diffuse into everyday objects as well. Even products can embody really complex ideas. Our digital experiments are materialized into physical objects, in this case using selective laser sintering, a type of 3D printing in nylon plastic, and also here in sterling silver using traditional metal smithing, but with 3D printed waxes. So it's time to switch gears a little bit and think about another project. And this one is looking at more how we can leverage these tools of generative design and digital fabrication to allow for personalization and customization of products. We already, as you've seen, work in this very process-based approach. Why not take the processes that we're developing in our studio and open them up to non-designers? Many of our design systems that we create are translated into online tools that people can use on our website to co-create products with us. So this project is called Kinematics, and it's one of those projects. In this project, we're trying to fuse fashion, software, and 3D printing to consider how digital fabrication and generative design can impact the way we create clothing. This project started with exploring a hinge-based 3D printed textile, essentially like this thing I have up here. We wanted to create a textile whose material properties could vary through space. So a textile that isn't just woven or knit, but that can have different rigidity, porosity, structure, drape, and shape all across its surface. We started to play with this idea with very small scale pieces that are approximately what you see up there. They were necklaces. And immediately we really liked sort of just playing with them, the tactile quality, how they have this hybrid behavior between being a hard material that's been made soft with all these hinges. So we thought about how could we take this material and make something bigger with it, like a dress, for instance. What if I wanted to wear a dress made out of this weird, hard, soft stuff? What would that be like? How would that sound? But immediately we hit a problem because part of the reason we were making things about the size of a necklace is because that's about how big a 3D printer is. The 3D printer is about the size of a necklace, so that's what I make. But if we want to expand past that and make this dress, how do we do that? So a lot of projects in the realm of digital fabrication get over this problem by chopping up their design into sort of like 1,000 unique bricks. And then a person will have to organize and manually assemble all those pieces into the final design, which actually ends up being sort of more time-consuming and difficult than any other part of the project, just that hand assembly. So they sort of have taken computation and make their lives harder. But we had an idea that maybe we could take advantage of the fact that our designs are flexible. What if we could find a smaller configuration of the design to make it in? Then we could, let's say, print the design in this small configuration and unfold it from the printer into its final larger shape. That's kind of cool, because if we can do that, it sort of starts to change the entire way you think about making clothes. Clothes are typically made of flat material, flat patterns that are painfully reconstructed into a 3D shape. But if we can make a garment fully in 3D, all in one piece, then we can start to think about designing directly off a 3D scan of your body, allowing you to design your own garment, and then 3D print the whole thing. Nothing ever has to be cut, sewn, or assembled. So in order to achieve this, though, there are a lot of different components that have to come together. We spent over a year developing the system to create just our first dress. Part of this included 3D modeling and physically testing dozens of different hinge designs. We also built a web-based design app where anyone can make their own custom-fit garments quickly and easily, which is what you're seeing here. You can play with this on our website. You start by putting in either your measurements or a 3D scan, so the whole time you're designing, you're working directly on your body. We also created a simulation tool that can be used to model the behavior of these complex structures in order to reduce their size for printing. This is based on a rigid body physics solver. And here we're showing the folding process for our first dress, which is sort of just folded in half twice to reduce the shape, the size by over 85%. Now that we have this robust simulation tool, we can use it for more than just efficiently packing the design in the printer. We can also use it to simulate the draping and movement of a garment before we ever print anything. So we have sort of a feedback between simulation and design. This video shows the printing process for our first dress. Except for it's not playing. There we go. And this was filmed at Shapeways factory in New York. We were actually extremely nervous as we were watching them excavate the dress out of this bed of powder, because we'd been working on this, as I said, for about a year, and we still hadn't printed a garment. We weren't sure if it was going to work. Would we have a sort of beautiful flowing dress or just a lump of plastic? And luckily, it did unfold, and we were able to make a garment using a 3D printer that required no assembly, that was wearable straight out of the machine. So what you're looking at is a custom-fit dress composed of over 2,200 unique pieces interconnected by over 3,300 hinges, and the entire thing is 3D printed as a single piece in nylon. While each component is rigid, in aggregate they sort of move as a continuous fabric, which allows the dress to flexibly conform and flow in response to body movement. Unlike traditional fabric, the textile isn't uniform and varies in rigidity, drape, flex, and porosity, and pattern through space. And most importantly for us, the entire piece is customizable from fit to style and flexibility and pattern. For us, this is just a baby step towards a larger project of thinking how can we leverage digital fabrication and co-creation to create complex digital materials and products. And how can we really empower the design process through these new digital tools? Currently, we're working with New Balance on a project that looks at how generative design can be applied to performance footwear. Can we use additive manufacturing to make shoes that perform and fit better? Towards this end, we've been designing midsoles for running shoes that are 3D printed in a new elastomer material. The structure of these midsoles is generated from data collected from runners. By placing a sensor inside their shoes, we can track how much force they exert as they run. This data is then translated into a variable density foam structure, similar to those seen in bones and wood. These structures can provide more support where more support is needed for each individual. So here I'm comparing a heel strike runner versus a midfoot strike runner. Oh no, the opposite, midfoot strike, heel strike. With this project, we're looking at how to take these technologies past art and design and apply them to creating performant functional products as well. Let's see, I wrote something here to say last. So I think what we're trying to do is explore how combining simulation and design can not only have this kind of morphological explosion of forms that we see that's very beautiful, but also open up design to more people. How can we take these techniques and not just use them to explore form for formalism, but use them to empower and democratize design? Thanks for listening. I have no idea what time it is, but I probably went over.